I gave, so thanks for coming. It's a talk in our workshop series regarding, oh, bloody hell. It's a talk in our series of workshops for the project of randomized. It's a series of workshops in our project of randomized methods for parameter-dependent problems, and it's also a joint seminar with Seminar for Numerical Mathematics and Scientific Computing. So this is my abstract and a conclusion of the talk. So what do you have here? You have here the question is, can you find an initial state in magenta that will evolve by a parabolic equation to the final state, which is this step function, but so that the trajectory is close to this indicator function for this period of time. So this is a constraint in time, this is a constraint in space where you need to get to, and the question is, can you find the initial condition, as in reversing a semigroup or computing a Laplace transform, which will get you there along this path. And you can actually, so here you see this is where you end up with this final state, which is the green thing, and then you have here an artifact of the fact that you needed to be close to wherever you were in the middle. You can play in this game in a sense that you want to have excellent reconstruction or excellent constraint on the trajectory in between. What this turns out to be is a convex optimization problem with constraints, and you actually solve it by doing a one-shot approximation, which allows you immediately, so you compute the optimum and then you project it on a constraint space as in terms of a proximal operator, and that gives you a solution, and you can write that solution using spectral calculus, which is what we do. So this is an abstract parabolic problem. A is negative definite with upper bound kappa, and you have a standard semigroup solution given by what variation of constant, which is an oxymoron if there ever was one. Okay, and the controllability here means that, so you say that it is controllable to target state y star. If this happens at time t, so obviously this is an operator which maps the initial condition to y star. And then, of course, you'd like to invert this. Okay, this is engineering-wise. The question is, how would you construct such a state? But apparently it was studied by Jacques-Louis Lyons, and then therefore it must be important. And mathematically, it's an interesting problem to try to see if you can do numerically spectral calculus based on rational functions. So proximal controllability, of course, means that, okay, I cannot ask for me to nail y star exactly, but can I do it with the epsilon tolerance? And actually, this is what's going to give you the constraint. If you are thinking about convex optimization, you have convex function with an equality or algebraic equality or algebraic condition or inequality, which tells you how this problem needs to be solved. And this is exactly how this linear constraint looks like. Quadratic, cost function is quadratic. You're looking for the initial state you had, which is the place where the minimum of this functional takes place, which is j, which is the smooth part, and then you have constraint, which is what's going to make it, it is convex because this is convex set, but it's not going to be smooth. So you have a regularization here, kind of Tikhonov type of regularization, and you have here a penalty on the discrepancy between the actual evolution and the evolution that you presuppose. So you say, I want this diffusion to go like W from 0 to t. And you can actually use this beta to give it a weight. It is something that you can use to, it's any L infinity function. Of course, those that we will be using are going to be piecewise constant. And for piecewise constants, because I mean, they are saying, they're kind of like switches. And for them, you can solve explicitly these problems. I mean, explicitly means write the solution as a function of a matrix so that you can use rational Krylov subspaces and a calculus with a numerical calculus with rational functions to actually give you an algorithm. So of course, a constraint problem can be written as an unconstrained problem by introducing an indicator function for this type of constraint, which essentially means that any u which is outside b bar, this ball is infinite. So of course you can relax it by making here a very large number, and if, according to free fem, a very large number is 10 to the power of 30, but that's not, it's called very large number truly with the acronym TVG, or VTG, sorry, value big, very big. I don't speak French, but you know, you can fill in your... Sure, but you don't want to actually. I mean, you want to implement this differently. This is just to prove the existence of the solution, because this extended function, it's convex and lower semi-continuous, therefore it has a unique solution. So you do know that there is a unique solution of this problem by standard theory. So sorry, what is this? Okay, this is the unconstrained problem. This is just introducing some notation so that we can use it to benchmark what happens when we actually do it in full generality. Relaxed version of the Hilbert uniqueness method has been used. Essentially, you solve you do forward solves of parabolic problems, and then you do CG somehow. So you're going to be solving a lot of forward problems, which means a lot of rational functions. I mean, time steppers are hidden rational functions if you do implicit Euler or some better evolved method. And you need to do it many times, because that is the operator which you are plugging in your CG approach. The question is, can you do it cheaper? Because, I mean, for CG to converge, you need a good preconditioner and whatnot. And you will be doing many steps. It's a joint work with Ivica, who I think is online, Martin Lazar and Martin Tautenan from Dresden now, I think, or Jena. It's a result of something that Lazar and Molinari and Papoket did in using the plane wave methods or eigenvalue expansions that we also talk about. But I prefer the numerical calculus, resolved calculus based on a rational Krylov toolbox of Berliaffa and Gütel. Okay, so what can you do? These problems, I mean, let's look for a sec at this problem, this one down here. So it's a convex problem. It consists of a smooth part and the part with jumps. So this is essentially an indicator function which is infinite outside the ball and 0 at the ball. So when you are in a ball, nothing happens, and otherwise you are out. The minimum of this will be achieved if 0 is in the subgradient of this thing, because it's not smooth. So J has a gradient, you can compute it explicitly, and this thing has a subgradient, and of course any of those would do if you were to do subgradient descent, but that would converge at best at the rate of 1 over the square root of k, where k is the number of steps, which is quite slow. And the subgradient for that, I think it's 0 between, well, for 0, when you're inside the ball, and otherwise it's anything that goes from 0 to infinity, because it can go all the way up. any of these lines will be below. So it's subgradient of a function is any tangent at the breakpoint. So anything that is below is a subgradient. So that's what you need to do. But that's not a condition. There is an alternative which says, how would you find the minimum of that? You can do a relaxation. You build a quadratic function which is higher than the function that you're optimizing. And the minimum of the quadratic function will for sure be above the minimum of the actual function. And they might coincide. Or you can do actually something else. You can try to optimize the smooth part and then just project it on the constraint set, which is essentially what the proximal operator does. So you find the minimum of the unconstrained problem, and then you compute the nearest point inside the ball to that problem. And actually, there is a formula for it. I mean, the most famous examples of proximal operators are, say, for nuclear norm, which is not smooth. Again, and there you have the so-called shrinkage operator for singular value decomposition, which solves exactly something like this. You have Frobenius norm squared plus the lambda times the nuclear norm, and the solution is the shrinkage operator, which which solves the problem kind of like this. It's slightly different here because the linear mapping is different, but for such problems, and having a characteristic function is a classical problem of this type, you have an exact solution. And here it is. So beta, recall, is input. This is a semigroup, and it essentially says, okay, so given the tolerance and the time horizon and the target, there is an optimal initial state given by this formula, but for it to work, you need to determine what is mu epsilon. This is a semigroup. This psi is an operator which can be defined by spectral calculus because this is semigroup of a self-adjoint operator. This beta is a function, so you know you can compute the spectral integral. And same for the vector psi. But there is this mu is defined as a solution as an intersection of this curve. No, this is a function of mu and epsilon. It exactly tells you when this phi hits the epsilon. Now what do we do? But this is a theorem. I'm not going to prove it. I have illustrated what it does. It computes the unconstrained problem and projects it onto the ball, which is essentially what this mu epsilon does, projects it on a ball. And then you show that it is indeed the optimal solution. Okay. I mean, but what happens, it's kind of geometrically clear. Now, how do we turn this into an algorithm? Okay, first there is the thing of beta, but if beta were piecewise constant, then I can actually compute this integral explicitly. I don't want to be computed numerically. I can actually compute it explicitly. And second, I can actually try to fit a rational function surrogate to the, by just sampling this function phi, for which again, I need to be able to move some semigroups, but okay, I can do that. Say maybe using the spectral calculus. And then for any tolerance, I will get mu epsilon, and out comes my optimum. So I just compute this surrogate once, and I solve a whole family, for a whole family of tolerances of these reconstruction problems. Okay, so in case beta is piecewise constant, this is what it sums up to, and this is how it looks in the spectral representation. And if you look carefully at this function is a difference of two functions which have a structure of the perturbed exponential function. Perturbed exponential function is a combination of a rational function, which should, and then exponential times rational, where this one should not be trivial, because otherwise you have an exponential plus a rational, and then it's not really fun, because you will be trying to fit rational with a rational function. I mean, okay, that can be done pretty well. I mean, there is nothing exciting about that. Okay. So what do we do? If you want to compare the action of your actual function g and its rational approximation, then it's easy that it comes down to controlling the L infinity norm of the rational approximant to whatever it is. And the best rational approximation satisfies the following bound. It says that there is a type nn rational function R such that the L infinity error is smaller than c times h to the power of minus n, n being the Macmillan degree. And this constant is 9.29 approximately. I mean, it can be computed explicitly. It's called the Halpern constant. And it's used essentially as the fastest way to invert Laplace transforms. Okay, so how do we come about constructing rational approximations? One way of getting rational approximations in a polar residue form is to start with Cauchy integral, and you turn it into a numerical quadrature. If gamma is nice, say circular, then trapezoidal rule will give you a very good polar residue approximation. Furthermore, if you have something in this form, it is very easy to evaluate the function of a matrix. They're just a bunch of shifted systems that you need to solve. Of course, there are faster ways, but theoretically, this is very easy to work with. So, Trefethen had a series of paper about Talbot quadratures, Karateridori, Fegere methods, and such. And it's sorry. Weber. Okay, he's. Major. Okay, sure. Yes, sorry. So the work started essentially with the inverse Laplace transform of a partial rational function, which allows you to deal with a semigroup. So how do you deal with that? In case your matrix is matrix, you can loop a circular contour around its spectrum, and then you do what you did. Okay, but our matrix is not. Our matrix is a self-adjoint operator, and when you refine, you are going to be closer and closer and closer to an infinite interval with your spectrum. So you don't really want a bound which will depend on how long this curve is. I mean, or to depend on a condition number. So what do? Well, you take a Möbius transform, which transforms this interval into a semi-infinite interval, and you apply it also to the trapezoidal nodes. And out comes, I think this is how the Talbot quadrature came about. So obviously they are looped here, but if you look at the resolvents you're integrating, then the decay away from this node is going to be pretty brutal. And that's why you can actually get away with nodes clustered here, approximating something which is very, very, very long on the real axis, actually even infinite, with an error which is behaving sort of exponentially in the number of these nodes. Recall h to the power of minus n, not for this contour. This is around 2 point something to the power of minus n. But let's not get there. So rational Arnoldi decomposition says the following. If you start with a matrix, you can write it in the so-called rational Arnoldi decomposition, where K and H are what Hessenberg matrices. And then you can write down your rational function as a polynomial times an inverse of a very particular polynomial given precisely by the diagonal elements of h and k. It's a very nice compact representation that Guttels and Berliaf's code computes for you while you sleep, as Professor Veselic used to say, and allows you to do other nice things, like, for instance, computing a rational approximation of this and computing a rational approximation of this, then adding them together and chopping what you don't need using SVD. And you still get a nice representation of the rational function as a Hessenberg pencil, with which you can then, do other things like plug in a matrix or whatever. it also allows you to do this pretty fast. Okay, yeah, there are two more here. Okay. So Galjorkin approximations, you take V to be a space of piecewise linear elements for a given triangular tessellation of omega. This is the Galjorkin projection. Of course, you have to take the integral formulation because piecewise linears are not H2 functions, so you have to work a little bit with that. But and then you have these shifts. So this C does depend on zeta, but these dependencies can be made rather explicit so that you can actually bound of what happens, you know, because you're going to be collecting this error over all these nodes that are scattered along your integration curve. I mean, this C is finite because it's a max over finitely many nodes, but you still would not want it to grow violently. And if your V is sufficiently smooth, then this is and the smoothness is measured with this parameter nu, then this is an estimate of the resolvent approximation. This is your Galjorkin projection, and this is the full resolvent. But anyway, you know, nice thing about this numerical resolvent calculus is that maxima or suprema over uncountably many nodes are substituted with something over finitely many nodes, and you know, it can be still a depressing constant, but it's at least something that you know you can sort of post-process. Okay, let me go here. Okay, where was I? Yeah, there. Okay, so the fact that everything converges, there is a book by Lasiecka and Trigiani where you actually do get convergence proofs for rational approximations of semigroups and whatnot. So there is a theory. I mean, you could prove it from what I've shown, but maybe, you know, in order to digest the proof that I haven't presented, it's easier to know that someone else has shown it to be true. So if you have your R in a partial fraction form, then obviously D is I guess N. You will easily collect an L2 error of the evaluation of your rational function. And then if your G is in a perturbed exponential form, then this is going to be exponentially decaying, even like 10 to the power of minus n. And then there is going to be the part, essentially the finite element approximation that comes out that you know how to reduce by amping up h. But at least whatever happens is as bad as any other finite element approximation of a parabolic equation. So yeah, the problem with Stefan Guttel's code is that we would prefer A to be written in a finite element way as a product of two matrices, which is you would have K, and then here you would have m to the power of minus 1 that comes out, and sorry, m, when you take out the inverse. That doesn't work. He only works with matrices and given explicitly as sparse in a sparse structure, because he uses LU factorizations to solve these inverses, and if you were to switch to an iterative method, then things would look differently, and maybe you can pre-compute things in a factor form, but he didn't do it. So lumped mass approximation is obtained in a way that instead of mass matrix, you take a diagonal matrix, which on a diagonal has the sum of the elements in a row of your mass matrix. It's very simple. You take any finite element code, you sum the elements on the diagonal, on each row, and you put it on a diagonal. It's a lumped mass approximation. Essentially, it introduces the error of the size of quadrature. So it would introduce here the error of the size of H2 nu. So, I mean, it's not changing asymptotics, but it's, I mean, you will see it. If you want to do something highly accurate, then you won't do that with lumped mass approximation. But on the other hand, you can use sparse direct methods without worrying about preconditioning and whatnot. Okay, so when your rational function, so it's my attempt at humor. Rather than let's making rational functions great again, I let them galore as in James Bond movies. So anyway, this is what you have in the middle third of your, so 2/3 and a third for this beta and omega. But the point is that you can actually compute the psi and phi for piecewise constants explicitly, and you could have more of them if you use like the Christian had the sum of characteristic functions. And then, of course, this is obviously a perturbed exponential for which you have good rational approximations. So let's look at the plots. So this is for small epsilon. For small epsilon, you reconstruct the final state pretty well, as you can see it here for final t, and you do not reconstruct your trajectory in any, well, you see that there is some constraint on your trajectory, but you don't see much. If, on the other hand, you say put it here half-half, then you reconstruct the final state, kind of, but you also reconstruct the trajectory in the meantime. And of course, you can be really extreme in saying, I don't care about the final state. I want to be, you know, I don't want to blow with my temperature out of the certain temperature range. Then I reconstruct that, and the final state, okay, there is a target, but we didn't really hit it. But at least the support ended up where it should be. Okay. Why is this cool? It's, of course, this you could do. This is just a validation experiment for Laplace. But if you had something where you have two materials in contact, then you can either compute many eigenvectors and functions like we are doing for Laplace, or you can actually do this. And, well, you see that there is two materials. I think they switch somewhere here, so they are kind of inclining a little bit to the right, so that you know that there is some jump there. But everything else pretty much works the same. So there is the loss of symmetry as it should be, but so the method can be trusted. Of course, given the fact that we had resolvents converging strongly, other situations where you have strong convergence, like for instance in a periodic homogenization, you will get the same effect of various level of this multi-level scheme. Anything converging strongly will converge strongly also. I mean, the functions of matrices will converge when evaluated on a vector. So it's a nice example, let's put it like that, because you can see what happens as the scales change for this type. So in 2D, of course, this is anyway. This is. Did I write down? Okay, I did not write down what I wanted. What was the goal? So the goal was to stay close to this ball and nail these three lumps, Gaussian lumps, concentrated here in the end. So this is low tolerance. I kind of didn't touch whatever happened here, and I ended up with some perturbations in the area where I wanted to end up. This is what happened. Oh, yes, sorry. This was what happened in between. This is for half a time, so where I should be close to here, there is some movement there, but very little. And then everything ends up concentrated here, almost perfect reconstruction. When I have half-half, then obviously there is something going on here, and but I still get pretty much close to what I need to get. So this is what happens in center, and this is at the end of the process. And then if I say I don't care about the end, then indeed that's what happens. You stay where your trajectory says you should stay for given time intervals. And well, with that, this is a Berliafa paper. This is the Journal of Approximation Theory, the Vargas paper about Halpern constant. And this is our work on Humboldt's equation and actually sampling the resolvent. And well, of course, this is my funding, and this is what brought. Yes, for the record. This is my funding now. So I'm very thankful to all of you and Creation Science Foundation. And are there any questions?
Just want to comment on FAIR.
Mm-hmm.
These PhD students,
Mm-hmm.
Paul Ehrlich, von Neumann,
Oh.
Gloria, Ries, Schaefer, Tekete, Lanzos, and many others.
So like anyone I mentioned is his student. Yes. Wow. Okay. I didn't know Lanzos. Okay. Wow. Okay. Good. Okay. Yes.
RK-Fit.
Mm-hmm.
Is that the only software that is available that do something like this?
I mean, Zlatko mentioned this vector fitting.
I mean, I think they did start these ideas from vector fitting.
Yes.
In a way, but vector fitting is the way that Gustafsson and others did it by really underestimating the Macmillan degree. Because they really have full-blown residues, like a full range system. But then you can treat it with SVD and perhaps refine that could, and then use this really high degree vector fitting as a middle layer because it's cheap. But it will match the original system like that. And it's a policy before, and you can do things.
I mean, you know, this idea of how he works this greedy surrogate is, I mean, it's nice to show, but that's not the main benefit of RK-Fit, the way I see it. I think the main benefit is that he wanted to implement the rational function version of Chepvan, that you can work with rational functions without worrying about anything, knowing that the sum will be truncated to a given degree and up to the full machine accuracy. So, and that you can get poles and residues and whatnot and zeros without worrying. You just say roots and outcome roots. And that, for instance, when I have these two rational functions, I sum them, and I'm certain that I got a reasonable approximation. So, I mean, like what we were discussing earlier was you had a sinus hyperbolicus and cosine hyperbolicus, and you actually want to sum them up. Maybe summing up their rational approximations would actually work better than summing than sampling directly from their difference and then fitting a rational approximation. It's this thing was done very robustly and very professionally by of course, as you expect from Stefan. And then there is the other thing, which is the evaluating the rational function of a matrix, which where he builds the Krylov rational Krylov basis, compresses it there, and then he applies the rational function. So that is done in a very optimized way and almost black box way. And yes, of course, there is the nice functions to plot and whatnot. It is a toolbox. So vector fitting is kind of, I mean, you have to work yourself. I mean, it is meant for an engineer. This is, as Mark Embry would said, Trefetenesque. So it's, it's very lovely. Okay, questions? This doesn't seem to be the case. And the perfect time, yes, even with me being late. And I had more slides than Christian and still managed to say everything. But I had many plots. Anyway, thanks.